we have everyone back. Everyone good with audio?
Think so?
I think so.
Awesome. Cool. Okay, hi everyone, and welcome to the special edition Dawn Hangout. This is Ceres, Great Expectations. So this is part 2 in our Ceres series. Yes, we are calling it that because why not? I am Nicole Gallucci. I am postdoc with the CosmoQuest Citizen Science Project, and I am joined by Brittany Schmidt from Georgia Tech. Hello. And I also have Whitney Cobb here from the Dawn EPO mission team, and she will be helping us track comments. And our 2 special guests today are Katie Dyl.
Hello.
Hello, Katie. And Andy Rivkin.
Hi.
And they are going to be telling us a little bit more about how we know what we know about asteroids and Ceres, and why we're so excited to be getting the Dawn Spacecraft 2 series in early 2015. So I want to let you guys know, if you want to send in questions or comments for everyone here in the show, there's a couple of ways you can do that. If you're on Twitter, you can tweet at NASA_Dawn, and so we'll be monitoring that, answering questions there, as well as sending them along to the Hangout. You can use the event page on Google+, for questions there, or you can use the YouTube comments if you're watching this on YouTube, and we will be monitoring all those places. So feel free to join in the conversation and ask any questions as we go along. So why don't we get started right off with Brittany? Wanted to give us a brief overview of Dawn and how it relates to Ceres.
Sure. So it's a pleasure to be joining you guys again. Last time we chatted, I got to tell you a little bit about kind of my interests in Ceres, and today we've got 2 really great experts and friends of mine. Andy Rivkin is at Johns Hopkins Applied Physics Laboratory, so in Maryland, and Katie Dyl, who is actually a UCLA grad who is now doing a postdoc at Curtin University in Perth, Australia. So Katie is a meteoriticist and Andy is a spectroscopist, and they both study asteroids and the early solar system using a variety of different tools. So we thought they'd be really great perspectives to share the story of Ceres and what we're looking forward to with Dawn. But for those of you who may be new to the Dawn mission, it is a spacecraft that has just finished up a little over a year of observations of asteroid Vesta. It's actually the first spacecraft that's gone to one target and then left that target and gone on to orbit another one. So we're actually in the middle of our flight to Ceres, which, as we mentioned, we'll get to Ceres in early 2015. Dawn is an international mission that actually involves investigators from the United States, from Italy, from Germany, and then a lot of people invested across the United States as well. So really great, awesome little mission. We're really excited to be bringing you the story of the science and kind of our outlook as we head into Ceres. So with no further ado, I'd love for the scientists to just go ahead and take over.
Okay. I don't know whether it makes sense for me to go first or Katie.
Sure, go alphabetical.
By which first or last name?
Oh, good point.
So I use telescopes to look at asteroids mostly, and to look at the composition, and we're going to, I guess, talk about mostly the composition of Ceres and some other asteroids today. So mostly I use telescopes. So, you know, I stay up all night doing that, and of course it's nighttime in Australia, so, you know, nobody's awake when they necessarily want to be awake. So the first, I guess, the first thing to show would be spectrum explanation human range. If you can slap that up. I don't know if I'm going to be able to tell if you have or not, but there you go. All right. So sunlight, and I guess all light, when in a sense, could be split into various colors. You know, people who have the old Pink Floyd album, Dark Side of the Moon, you know, there's the prism, and the white light comes in, and the rainbow comes out. And you can measure light by and measure different colors by the energy that the associated color that's associated with that color. and that's kind of shown along the bottom of the plot here, wavelength. It's not exactly energy, but it's related to the energy. And then across the top there are color bars, and that shows where the human eye sees the different colors from violet on the left through blue, orange, yellow, etc. to red. And there are different materials that you may be familiar with on this plot here. In the green kind of line there is just normal green paint, and that reflects, the y-axis there is reflected light. That reflects more light in green, the green part of the spectrum, than in other parts of the spectrum that we can see, so we see it as green. The red brick there, similarly, reflects more light in the, I'm pointing at the screen, and this probably looks silly to you. I know what I'm pointing at here. The red brick reflects more in the red than in other parts of the spectrum, so there too it looks red. The two other kind of materials you might be familiar with, the white marble on the top and the gray shingle, those both are pretty similar in that they reflect similar amounts of light across a lot of different colors, but the white marble reflects a lot more of the light than the gray shingle. So we also have two asteroids on here, Vesta and Ceres. Vesta was the first target for Dawn, and that's shown the blue line there, and then Ceres is the black line way down there at the bottom. So Ceres, to the eye, would appear basically pretty black. It's reflecting most colors more or less the same, and reflecting not a lot of that light. So this doesn't tell us a whole lot about the composition in this wavelength range. So if you could show the next one that talks about the IR, the spectrum explanation IR, and when you go beyond what the human eye can see, we have instruments that can measure out kind of at almost any wavelength we want. And now we start to get some more information that we can interpret more easily. You start to see kind of what we spectroscopists affectionately mostly call the bumps and wiggles out here. Vesta now shows a couple of broad dips, and if you look at the y-axis at about 0.9 micrometers and about 2 micrometers, and we know from looking at other materials, both here on Earth and in the laboratory, that means there's specific kinds of rock out there, specific minerals like olivine and pyroxene. You can also use this for some of the other materials. The green paint, for instance, has little dips at about 1.7 micrometers. That's probably due to organic material, some kind of fixer in the paint. And at 2.3 microns, there's another dip there that's probably due to clay minerals. Again, that's a fixer in the paint, or something that's used in the paint. Through these wavelengths, Ceres, you're still not really getting too much. It's still pretty flat. So that still doesn't help us. So we have to move even further for Ceres, as opposed to most asteroids like Vesta. So we had a good sense of what Vesta was made of 10 or 15 years ago when these sorts of measurements were made. I don't know if Katie wants to jump in and talk about Vesta meteorites as another part of that.
I can. It might be a good point because I can take you up to the same spot, or I can take everybody else up to the same spot you did, which is, sort of right up to why we're interested in Ceres.
Great. Knock yourself out.
Great. So if you want to show my first slide. So for the first slide, I just wanted to show people sort of to first order why we care about meteorites in the first place, other than the fact that they're from space, so obviously who wouldn't want to study them for a living. But there are two primary reasons, or rather two different types of meteorites that give us information. So one type of meteorite, for example, meteorites that are solid iron metal, they tell us what planets were like in the early solar system. So many of our meteorites are actually bits of things like the Earth's core, except unlike the Earth, they didn't survive, they got broken up, and we get the pieces today. But there's a second type of meteorite, these are broadly called chondrites, and they're of particular interest because they tell us what the solar system was like at the very earliest stages. So the meteorite I have there in the picture is called Allende. It fell in Mexico in 1969, and you can see there's sort of a black, almost cement, what we call matrix. And within that matrix are a lot of round spherules, which we call chondrules, a lot of weird shaped white things, gray things, and all sorts of other fascinating inclusions. But the reason why meteorites like Allende are important is because the sort of white or gray blobs tell us what we think the solar system was like at the very, very earliest stages. So right as the sun was forming, right as rocks started to form in the solar system. So that's sort of what, how we learn about the very earliest stages of how planets form. And the chondrules, which are the circular sort of minerals like olivine and pyroxene that Andy was talking about in his spectra, we think those tell us about processes that are happening somewhere in the disk of gas and dust out of which planets form, but depending on who you ask, they mean different things and come from different places. And then finally, the matrix, which is the black material that makes up a lot of these rocks. We think it comes from farther out in the solar system, but we really don't know that much about it because it's very fine-grained, and when things, when planetesimals grow, like Vesta or Ceres, and get big, those really fine-grained materials are sort of the first things that end up being changed and altered. So if you want to go to the second slide, this just gives you an idea of the specific sort of asteroids, or meteorites rather, I'm interested in, and the ones that we might start thinking about when we go to Ceres. And like Andy was saying before, Ceres looks mostly black, and as you can tell from the 3 pictures there, those meteorites are also pretty much black, not too much there. And the differences between those types of meteorites are how much water we think melted and interacted, or how much ice melted and water interacted with the rocks as they were floating around in space. So not weathering when they land on Earth, not anything that happened yesterday or even 100 million years ago. All this stuff happened 4.5 billion years ago when the solar system was forming. And so that's my particular interest, is sort of thinking about what water and rocks are doing when planets are forming. So this slide here gives you sort of our metric for how we classify meteorites based on how much water's interacted with them. So at the far right, under green, you see Allende, and that sort of mineral inset there is a mineral called olivine, which again Andy mentioned, and olivine is pretty much what makes up most of the Earth's mantle and makes up a lot of other meteorites as well. And the second sort of meteorite in the middle there under the aqua or cyan is what we call a type 2 meteorite, and that meteorite is called Murchison, which landed in Australia in 1969. So between Allende landing, Murchison landing, and the Apollo missions to the moon, people had a pretty exciting year that year. But in that case, we actually can see minerals like the mineral on the inset there called serpentine, which you might also know as asbestos. And we know that forms when water and rock interact at lower temperatures. And then finally, at the very left there, under the dark blue, is what we call a type 1. And those meteorites are almost completely altered. We don't even see chondrules anymore. They're just balls of black clay. And again, you can see sort of the inset there for one of the minerals. It's pretty prominent. And that meteorite that's shown there, it's called Orgueil, and it fell in France in the 1800s. So even way back when, people were studying it and trying to understand what it meant and where it came from. And ironically enough, we still don't actually know. But that's pretty much the spectrum you have there, from things like Allende, which we think preserve all those different components from nearby the sun, at the very earliest stages of the solar system, up until what water and rocks are doing together on, bodies maybe like Ceres, and down through things that have been completely altered. So that's kind of where Andy and I tie in together, is For example, how we learned that we have meteorites from Vesta. People, like Andy, measured the spectrum in space, and people like me took meteorites in the lab and measured the spectra, and they're exactly the same. So can't quite do that with Ceres yet, but that's why it's really interesting to actually go there and get a better look.
So yeah, this is one of the few places in astronomy where we can physically sample the things that we're looking at, right? Is that we actually can get samples, but for Ceres we don't have any samples that we know of.
Yeah.
So we're just using the light. So we're using spectroscopy, which is a very powerful way of finding out what things are made of, to look to see what it's made of. Of course, at this point in the story, we haven't learned much from the optical and the IR spectrum. We're just getting a very flat spectrum, a very dark object.
Yeah, and lots of ideas from meteorites of what might be there, but
what it could possibly be.
Yeah.
I want to remind you guys watching, this is the Ceres series, Dawn Hangout, Great Expectations. We're learning about how we find out what we know about Ceres so far from spectroscopy, and what we think we know about asteroids from meteorites that we have here that have hit Earth. And so there are a couple ways you can ask questions. Please feel free to use the Twitter at NASA_Dawn. You can ask questions there. I know Whitney and Judy are watching that. We have a link that I've added to the event page, which I will, it's not on, I can't share links as well on the YouTube, but I've put on the event page, where there is a brief survey. I don't know if we want to talk about that now or save that to the end, Whitney. So we'll we'll save that till the end, but we'll let you guys know that link is there because we're doing a survey and a giveaway at the end here. So be sure to look for that link, and please use the event page for comments and YouTube page for comments as well. So I don't know, Katie, if you had another point you wanted to make right away, or do we want to move back to Andy on this spectrum mystery?
No, I think going back to Andy is perfect at this time.
Okay.
Okay. So the spectra that I was showing before, out to 2.5 micrometers, that's the most common spectral region. When asteroid spectra are taken, that's usually how far we go out. There's a lot of instruments that can do it. It's very convenient, but it hasn't given us much for Ceres. So there are instruments that can get us a little bit further. So this would be the Ceres spectrum plot, image thing.
Sorry, I'm a bit slow on the internets today.
Not a problem. Not a problem. So this just shows Ceres alone, and it takes the wavelength region from the previous plots. It expands it a little bit further out to the right, and it really zooms in on the y-axis. So you can see that we're talking about differences of, where it'll reflect 7% of the light instead of 9% of the light. So we're really talking about really stretching the image, as stretching the colors, so to speak. And it turns out that there is a little bit in there if you really stretch it out. We see, again, at about 1 to 1.5 micrometers, there's kind of a dip there. We think that's due to oxidized iron. Maybe something like magnetite is the mineral that people might be familiar with on Earth. Although, as I'm not a rock hound, I don't know how familiar people might be. I think magnetite is the black little specks. If you go to the beach, and you have a handful of sand, I think the little black specks are magnetite. There's a gray region, and it's a very important region. That's where you find absorption features and these bumps and wiggles due to water. And unfortunately, because of water in the Earth's atmosphere, it's very hard to get that data. In that gray region, we actually had to use data from a satellite in space to get that. And we do see evidence of OH on Ceres, probably like these kinds of clays that Katie was talking about in some of these meteorites. And then there are a couple of other features in here again. Some brucite there is a magnesium hydroxide, and that's something that's not really found much in the meteorites, but we do certainly seem to find it on Ceres. And then two other features that we think are due to carbonate minerals, which makes Ceres one of only a few places where we've found carbonates. I think other than Earth and Mars, it's Ceres. So this starts to let us put together an idea of what is present on the surface of Ceres, and then that lets the geochemists go ahead and say, okay, how do you make these things? What kind of environment do you have to make something like brucite, to make things like carbonates? And also, to go back and rule out, okay, it doesn't look like Vesta. We think we know what happened on Vesta. There was some sort of melting of rocks and maybe some lava coming out, and we don't see those minerals on Ceres, so that suggests that didn't happen on Ceres. Again, consistent with what we see in the meteorites, at least some of the meteorites. But we are pretty sure we don't have meteorites from Ceres itself, so we're missing that link that we had for Vesta to be able to say, to put it all together. So Dawn is really going into new territory in that sense.
So Andy, just a really quick question. Why is it so exciting and so different that Ceres has all this stuff in the IR? How does it compare to other asteroids?
There are the meteorites that Katie's been talking about, the carbonaceous chondrites, that have these dark clays. They don't really have things like the brucite or a lot of the carbonates. I guess they'll have some. What we think formed these minerals on Ceres is that there had to have been a lot of water, and that water interacted with the minerals in a way to form the brucite and the carbonates. We think that the carbonaceous chondrite meteorites have been pretty much left alone since they formed. There hasn't been a lot of real large-scale chemical reactions going on. That they're more or less as they were. For Ceres, we think it's much more consistent with a body that had a lot of water available to interact with a lot of rock. I don't know if I'm saying that right. And it's also interesting because conversely, we see no real evidence for ice at the surface of Ceres. Ceres is just way too warm to keep ice at the surface, but there's all this evidence from observations by Hubble and theoretical work that there's a lot of ice in Ceres. So that creates this interesting paradox. We think there's a lot of ice there. We don't see any at the surface. How that's going to translate into what we find when we show up there is still very much an open question.
Yeah, that's an idea that was really bizarre for me. Last time we talked about this, because you think of icy bodies being in the outer solar system, moons around the giant planet, the gas giants, or out in the Kuiper belt. You don't expect to find something like that, not only in the asteroid belt, but the largest member of the asteroid belt.
Yeah.
And yet it's yeah.
Yeah, I mean, we even just know from density arguments that the density of Ceres is low. It has a density that suggests it's about 1/3 ice by mass, and certainly 15 or 20 years ago, when we started grad school, or some of us started grad school, the idea was that there wasn't really much ice interior to Jupiter, and there's been a lot of work from dynamics and a lot of, at least some evidence that a lot of material has really moved around in the solar system, and at least one serious senior member of the community suggested Ceres formed out past Neptune and got transported all the way in. I think that the evidence is against that. He suggested it a few years ago, and I think evidence has mounted since then that it's not the case. But it really has appeared to be a fish out of water. No pun intended there. There do seem to be other large asteroids that have similar spectra to Ceres. We don't have nearly as much data But if you follow the chain of logic and you say, okay, Ceres' surface is the way it is because of its history, and its history is that it has this big ice shell over a rocky core, then you might think this has happened a few times in the largest asteroids, and that starts to then make Vesta look like the odd duck.
Yeah, so Katie, you must have some perspective on that, because part of the reason that we thought that way back when Andy was mentioning at the beginning of his grad school days was because of meteorite studies, right? Was that we were kind of forcing things into a rather small box, as it were. So I was wondering if you would share some of that perspective.
Yeah, no, I was actually going to say some of the things Andy brought up. I guess I don't know how the Hangouts work. You can either bring up my third slide or I can just talk. But it's actually, so I think it was 19. Well, actually, the first paper. So yeah, I can't do math right now. It's 1:30 in the morning here. But anyways, yeah, sort of some of the stuff I'm working on is really thinking about, what Andy said, right? Okay, we think that nothing much has happened to these guys. They're from smaller bodies and things haven't moved around that much. And really thinking about how true that is. I think it was suggested a couple of decades ago that there could be fluid flow on these bodies, and now people think that they might convect, and really what do the meteorites say, and how can we sort of use meteorites to constrain some of these models. So this picture is a picture from a billion-dollar instrument called a synchrotron. So there's one of those in Australia. And it also happens to have the one detector in the world that can map elements across whole meteorite sections. So this is a section of a meteorite, and it can basically scan along this guy in a couple of hours and get trace elements and all sorts of other interesting chemical facts. But this is a map that's created by combining the distribution of several elements. So green is iron, and red is nickel, and blue is chromium. And so what you notice right away in Vigrano, which is sort of like Allende, the meteorite eye, was the carbonaceous chondrite, thank you, Andy, that I was talking about earlier. We think Vigrano is kind of stable, one of the not too altered meteorites. But even here you can tell, well, number one, that the nickel, which is the red, is obviously moving around. And it's moving around in the same direction. So the sort of a blob at the upper right-hand corner is traveling, roughly parallel to the two blobs that met just below it. So you wouldn't be able to, those differences in the elements are sort of hundreds of parts per million. So it's really hard to kind of detect those differences any other way. And you can tell also right away that there's unaltered material here. So things that are still very heterogeneous and kind of broken up, but also these veins of altered material that's been fairly homogenized. And this is something that we obviously didn't really expect to see when we decided to see what meteorites look like with this new technique. And then if you go to the next slide, which is one of the meteorites that we think altered at lower temperature, so the serpentinite type ones. And so when Andy was talking about carbonate and brucite and meteorites that have hydroxyl groups or water attached to them, Murchison is the exact sort of meteorite you'd want to be thinking about, because this is the meteorite that has lots of carbonate in it. It has minerals similar to brucite, although not exactly, and it definitely has a lot of OH groups. And this is a very similar image to the one before, except blue is zinc this time. But you can see again, there's very different sorts of textures that you can see in these elements at very, very fine scale. And the reason why it's not more obvious is because it's at such low temperature to begin with, and these meteorites are basically fine-grained, completely black, right? So much like spectroscopists have a really hard time with things with spectra that have no features, that look pretty black and flat, we have a really hard time with meteorites that are very, very fine-grained, that are really hard to sample and prepare and look at. And so what this image is showing you is that you kind of have the spongy texture that's brighter green, but then you also have textures that seem to be showing more discrete detail in things like iron, and also around the big black spots, which are not empty spaces. They're minerals like olivine, for example. So olivine's also present in these guys. But you can see that there's sort of elements moving between larger rock pieces and whatever water rock mixture they sat in at some point in time. So I guess what I just wanted to show you with those two is, one of the things we're really starting to think about in meteorites lately is, what sort of object did they come from, and could they be from something like Ceres that's big? What do we really know about the material that makes up Ceres? Are they from something that's much smaller, like we thought a couple decades ago? Yeah, I guess it's just what's interesting to me is just like sort of all of these different communities with the missions that are going out and all the new technologies that are in context, and potentially revealing insight as to whether they were from much like iron meteorites, right, that are cores of internal objects that completely split up and were big at one time. Is that the same thing with carbonaceous chondrites? Are they from big objects too, or does the fact that the chemistry is so uniform mean that they had to be from smaller stuff? And you can just kind of go to bigger and bigger questions from there.
Sorry about that, guys. I just dropped out briefly, and I don't know if that interrupted the broadcast, but we have everyone back. So I just wanted to say that these images were really awesome because it's this tiny, tiny, tiny close-up look at some of the oldest things in the solar system, right? These are the time capsules of the first things that formed in the solar system, and this is what we think that Ceres may hold in store. Is that correct? Yeah. Very cool.
Yeah, so my favorite analogy for carbonaceous chondrites is that they're the vacuum cleaner dust bag. So if you lived in your apartment and, didn't vacuum for a long time and just kind of hung out there for a couple million years, and then somebody came and vacuumed up, and then, a couple million years later, it became a rock, and then you could dissect, what you ate at all the different points in time. So I kind of view carbonaceous chondrites as very similar to that. It's kind of like the vacuum cleaner bag from the whole solar system.
Oh
That's totally going up on social media.
You know my vacuuming habits too well.
A lot
I've been using that analogy for a couple of years, and it hasn't stuck yet, so...
We're going to make it happen, because that is a really fantastic analogy.
Oh, thank you.
Okay, so what more? What more do we know about Ceres? Even though the spectrum is kind of difficult to see, we can only see these few percent changes, and we don't have a, we aren't sure exactly which of these physical pieces it's most like. What else do we know about Ceres so far? Anyone? Anyone?
Well, sure. We have, as noted, we have a decent shape model and a decent density for Ceres.
Right.
And given that, people with computers can just go and run all sorts of directions, right? So starting with the kind of starting material we think Ceres would have begun with and would have begun in the asteroid belt, you can go forward and say, okay, you have so much radioactive material, which means you have so much heat being generated, which means that the temperatures get so high, which means, etc. And so that's why we have this. That's why we have this idea that Ceres has a kind of an icy shell over a rocky core, and yet I think I mentioned this. It's the surface of Ceres is too warm to maintain ice, and yet we think we have this ice really close to the surface. So you can end up with this situation where ice may be lurking just a few meters below the surface, but the surface itself really can't have a lot of ice.
It's the Mars of the asteroid belt.
Yeah, in a sense, yeah. It's by far the biggest object out there. It has like a third of the mass of the asteroid belt all by itself.
Sorry. Andy, what instruments do you use? So we have Dawn that's on its way there, but what instruments have you been using to get these spectra of Ceres?
A lot of the spectra of Ceres that I've been showing, and most of the asteroid spectra we take these days come from the SPECS instrument on the IRTF, and I'm sure somewhere lurking around there you have a picture of that.
Is that what Brittany's showing? Yeah.
That's what Brittany's showing. Yeah. And it's on the top of Mauna Kea, which is the best observing site. It's generally considered the best observing site in the world. Some other places might argue, but that silver dome there is the IRTF. This is looking north, so Maui is the island in the distance there, and we use a spectrograph called SPECS. It's been online since about 2001, 2002. And it's going for an upgrade now, and it's supposed to come back next year, even better than before.
So up Mauna Kea is a fairly extreme environment. I haven't been there myself, but have you visited there, or where do you normally observe from?
I have been there a lot, but it was good for the frequent flyer miles. But it's at 14,000 feet, so it's not great conditions for thinking or breathing. Or much of that. The sky is beautiful up there, but for the past sort of 6 or 7 years, they have remote observing capability. So I actually sit right here where I'm sitting now, usually, although I'm wearing my robe at the time when I'm observing nowadays. And I figured I'd put on a shirt for you guys at least.
So you're the Arthur Dent of astronomy, basically.
That's right. No, I don't usually bring a towel though, But that's been working well, and that's kind of a win-win in general, because it saves NASA and NSF money if you can do it from your desk or wherever you are, and it kind of saves on time, because now instead of making it a long trip where it takes a day to get out there and you have to acclimate for a day, and then it's not worth getting less than 2 nights of observing at a time, you can really fit in and say, okay, I only need 2 hours. Just give me 2 hours. Roll yourself.
So yeah, this is sort of the standard thing I look at. So this is a rock from space, scientist style, I guess. But I use a lot of electron microscopes. So they're microscopes not like the ones you're used to thinking about for biology, for example, but $500,000 to $1 million machines with fancy new optics and field emission guns, and I don't even remember what the detectors are made of, some other new ceramic. But long story short, in the last decade, they've come out with a whole new type of instrument. So if people work really hard, they can see, like I was saying, the carbonaceous chondrites are nanoscale. So basically, an atom. So basically, most of the grains in Murchison, for example, are 10 atoms across. So these instruments can actually image things that size. And there's all sorts of other new techniques, and that's actually one of the nice things about moving to Perth, which is in Western Australia, which, for those that don't know, is largely supporting Australia's economy due to the mining industry. So there's a lot of research capability, a lot of instruments, a lot of geologists, a lot of expertise, and one of the things I really enjoy doing here is trying to talk to those people from different backgrounds and see what I can apply from sort of their knowledge about how water and rocks interact to form a gold deposit or an iron formation, and see what that tells us about meteorites. So that's one of the benefits that was unexpected about moving to Australia about a year and a half ago, I guess.
Very cool. So now you're using this expertise from earthbound geology, and we can go back to space for a bit about where, I think we talked a little bit about where carbonaceous chondrites come from and what they are. Maybe you can expand a little on that concept.
Yeah, I think it's slide 5 is the one I sent you.
Sure.
And part of this slide was just me being really fascinated by just how much we've learned in the last couple of decades. But the point of it can be summarized as there are a lot of theories about where carbonaceous chondrites come from, but we still really don't know. So depending on who you ask, and I would say it's at least 75-25 probably. Some people think they come, or we know a lot of them come from the asteroid belt, but carbonaceous chondrites themselves, are they asteroids, right? Are they something like Ceres, for example? Or a lot of people think that they could be comets. So, yeah, in this case, I just thought it was really neat that in 1974, that's what we thought of as a comet. And now, thanks to Stardust, which was the mission that brought back pieces of a comet, we have a much better idea of what they look like. And actually, when we look at those little grains from a comet, they're grains of things in meteorites. So, very similar, I guess, in terms of, the minerals you might expect in a carbonaceous chondrite. And then I think Brittany mentioned this in the last episode of the Ceres series, that recently it's been discovered that they're main belt asteroids, so asteroids in what we think of as stereotypical orbits, but they have ice in them, and if they get hit by an impact or something else happens to them, they look like a comet would, except unlike comets, which go out to Jupiter or out into the Oort cloud and then back towards the sun, these guys just kind of hang out in their standard orbit and still display this evidence for water. So it really kind of blurs the lines of what's an asteroid in the first place and what's a comet in the first place.
That's interesting, because I was just at Dragon Con and got the question, of course, what makes a planet not a planet, and what makes it a dwarf planet, and I explained there's a continuum of objects. And it seems like it's kind of the same thing in asteroids and comets. There's a continuum, or not a strict delineation of ice.
Yeah, I think I mean, it's one of those things where I think more stuff is getting filled in between. Mm-hmm. And, like even with Ceres, thinking of it as a body with a lot of ice on it, but, as I think Brittany and Andy mentioned, it's this perfect sphere. So we usually think of planets differentiating as iron goes to the center and then there's a mantle, but now there's this idea that a rock is a core and the ice is the mantle, and then what's the crust of something that's a water rock differentiated object?
Yeah.
And
so yeah, Andy, do we have evidence of water ice or ice on other asteroids other than Ceres?
Funny you should ask. We do, and in fact, it's related to the main belt comets that Katie just mentioned. A little further out from the sun than where Ceres is. So Ceres is at like 2.7 times the Earth's distance from the sun. When you get out to like 3.1, 3.2 times Earth's distance, you can start to have ice be stable at the surfaces for a little while of some objects. And we did find a couple years ago on an asteroid called Themis, asteroid number 24, evidence of ice on its surface, an ice frost. And Themis is part of an asteroid family, so the original body was maybe about half the size of Ceres. It got pounded by a big impact, and Themis itself is the largest. The asteroid 24 is the largest remaining remnant. And some of the other smaller members are actually some of these main belt comets. So it all hangs together that the original body had plenty of ice, or at least had enough ice that it exists today on the surface of Themis and as some of these main belt comets. We've also seen ice a little further out from Themis, so out at, once you get out to 3.3, 3.4, 3.5 times the Earth's distance, we see ice more commonly on those objects. And then, of course, once you get far enough out to the distance of Jupiter, the Jovian satellites, which are not asteroids, things like Europa, Ganymede, Callisto, those all, it's plenty cold. You can have ice on their surfaces, and we do see that.
Yeah. But Ceres being so close, it's not sure whether it's on the surface or not. And so I think you have some graphics I wanted to show about where this ice could possibly be on the surface.
Sure. Yeah. Why don't you show the one called lag deposit?
Sure. Do that.
So Ceres has a very low obliquity, which is the angle between its orbit and its pole. The Earth's obliquity is 20-something degrees, 22, 23 degrees, and that's why we have summer and winter. Ceres' obliquity is almost zero, so it doesn't really have much in the way of seasons. But it also means that very close to its pole, you can potentially keep ice. We don't have the resolution, the spatial resolution to see. And again, I'm doing this thing with the hands to see if there's ice near the poles of Ceres or not. Dawn will definitely get that information. For the rest of Ceres, closer to its equator, it's too warm to really keep ice around for very long. So we think what might have happened is one of a couple things, like in this plot here. So when Ceres formed and it differentiated, like Katie said, we think maybe into an ice mantle over a rocky crust. The very top of Ceres would still potentially be rock, and that would be heavier than the ice. So we think that would kind of sink down through the ice and the water. That would put the ice on top. But you can't really keep the ice on top because it's too warm for the ice. So that ice would then start to sublime away. For those non-scientists out there, basically evaporate, but evaporate means something technically different. So it's about start to sublime away and leave whatever kind of maybe collected in the ice behind. So we think that would be one way you'd get sort of these brucite and carbonate minerals at the surface of Ceres, is by leaving what we call a lag deposit. The ice would go away and leave whatever junk had collected in the ice behind. So that's one possibility. The second possible way of getting this brucite and carbonate on the surface would be the other plot, which is cryovolcanism. Cryovolcanism is a kind of specific term, which basically means volcanism, except you use ice for the magma and the lava instead of rock like we see on volcanoes here on Earth. And here the idea would be that you kind of have still a rocky crust, or some kind of crust, but if you manage to punch holes in that via either impacts or just the natural extensional stresses that you'd find, you might get ice to come up through that hole and kind of have an icy magma, an icy lava. And then you have the same situation where the ice maybe drags stuff up with it. It's too warm to keep the ice on the surface, so the ice goes away and leaves the stuff it dragged behind. So hopefully we'll be able to determine which of those two things is going on Ceres. Certainly when Dawn shows up, it'll give us a lot more data, a lot closer images, and hopefully that'll help us out.
Yeah, again, cryovolcanism is something that you see much more on the moons of the outer solar system, and so that's, again, a really interesting concept that we could find it in the asteroid belt so close to us.
Yeah, Ceres is in a lot of ways a lot like a like the icy satellites of the outer planets. It's just not orbiting anything. It's intermediate. Yeah, it's larger than Enceladus. It's between Enceladus and Tethys in size. So it's the right size to have some of this stuff going on that some of the icy satellites have. It's kind of free range, on its own.
It's doing its own thing.
That's right.
Yeah, very cool. So we are close up on an hour. I wanted to go over a couple of points. First, I'll have Whitney talk about the survey, then I'll go over some of our upcoming Hangouts, and then I would like to end on Andy and Brittany and Katie, our experts here, to tell us a little bit about maybe what they're most excited about seeing when Dawn gets to Ceres. So first, I'll start with Whitney. If you want to talk a little bit about the survey, I think you need to unmute yourself quickly.
So I had a couple of things I wanted to share out from Dawn EPO. One thing is that we would love to have your feedback on Google Hangouts, what you'd like to see that has, they're related to the Dawn mission, and both, what we are learning, because the science at Vesta is ongoing. Our scientists are still poring over a massive amount of amazing data we glean from that. You, as citizen scientists, can participate in some of that through our Asteroid Mapper citizen science project that we've developed with CosmoQuest. But also, of course, we're thrilled and excited to be headed to Ceres and cruising now quietly but swiftly through the main asteroid belt for that great dwarf planet. So we have a very simple survey, and what we'd like to do is invite you to take it. It'll take 5 minutes or less of your time. Just give us a little feedback and direction on what things you'd like to hear, and in return, we will send you one of our beauteous Dawn calendar. Katie and Andy have both already signed up for one, so we're sending them as a thank you present for their awesome participation today. So let me give you, I'm going to go ahead and, let's see if I can screen share this.
Cool. I've put the link on the event page in the comments, and I've also put a somewhat butchered version of the links in the YouTube comments since they don't allow direct links. So
perfect.
You could check those as well. Yeah.
Right, and I will certainly post on Facebook and all that kind of good stuff.
Excellent.
So here we go. Here's our link. We got a bit.ly link there because this link is about 2 feet long.
That's much easier than the one I typed in.
You've got it there, and we'll also post it in all those other good places. And the last little bit I wanted to make sure you're aware of is that we have some wonderful blogs that are part of the Dawn mission, and we have Mark Raymond's Dawn Journal, which comes out every month, and he really started that at the beginning of the mission. And we have a new science blog, and we love luring people like Katie and Andy to write pieces for that. And we also have some of our educational pieces that are going to be coming up. So we have the science blog as well as Dawn Journal as opportunities for you to engage with us, and of course, social media. We love to hear from you. So that's it for me.
Over on CosmoQuest, we're also working on an educational unit for middle school teachers to use that goes along with the Asteroid Mappers project. It's called Investigate. I love it. I love the pun. I did not come up with that, sadly. We previewed some of it at DragonCon in Atlanta, Georgia this past week, as well as showed people the Asteroid Mappers interface and had them marking craters right there at a sci-fi fantasy convention, which was really fun, showing them how bizarre and weird that world is. And so we're excited to have you guys as part of the citizen science, and especially if you're an educator, look forward to the Dawn already has some really great educator resources, and we'll be coming up with some new ones as well at CosmoQuest. As far as Hangouts are concerned, we have the weekly Space Hangout is tomorrow at noon Pacific, so again, apologies to all those that we missed last week because Fraser was at PAX and I was at DragonCon, and the Hangout got lost in the shuffle. So we'll come back with 2 weeks worth of space news for you guys tomorrow at noon Pacific, and then Sunday is the virtual star party. I think they're going to shoot for 8:30 Pacific. It's starting to get earlier as the northern hemisphere heads closer to autumn. So we thank you for joining all our Hangouts and for joining this one, specifically the very special series. And now like I said, I'd like to end with all of our experts, Andy and Brittany and Katie, if they can each give us a little bit of what they're most excited about for seeing when Dawn gets to Ceres in early 2015. So I'll start from the left again, Andy.
Well, I guess selfishly, since I've written a few papers on Ceres recently, I'm hoping to find out that all the papers are right.
Of course.
Because you never really know. But I think it's going to be a great target. I think it's going to be really interesting to see how something that all our evidence is that there's a lot of ice there, probably real close to the surface, and to see how that plays out in terms of the geology of the surface, how it plays out in terms of what we can learn about the history based on where it keeps craters, where it doesn't keep craters. There's a lot of work that's been done on how a warm icy body will retain or lose geological features. So I think that's what I'm looking forward to.
Very cool. Brittany, I know we've heard your excitement before, but I want to hear it again.
Oh, sure. Oh yeah, I mean I am similarly excited for the surface geology. I think Ceres is very different and very exciting in a lot of ways. Totally different from any place that we've been, and I'm looking forward to seeing how strange that surface might be. But I'm also really looking forward to the gravity data, which is where we'll really know what Ceres is made out of, in terms of its density distribution. But really, that's going to be the confirmation that we've got an icy satellite right there. So, or an icy, something like the icy satellites, but maybe the only primary icy planet that's out there, at least within reach of the Earth. So that's what I'm really excited about.
Very cool. And Katie, I know you have Ceres as well as some other stuff about linking meteorites and asteroids.
Yeah. Oh no, I can just finish up. Yeah, because
sure.
As I told Brittany, I made extra slides just in case. But in terms of what I'm excited about, I guess one is I have a favorite mineral, kronstatite, and it's ridiculously rare terrestrially, but is the main mineral making up things like Murchison, so the low temperature meteorites. And I want to know if that's on the surface, because it would be awesome. And the other thing, which I guess echoes what Brittany and Andy were saying, is I guess, and this can also serve as a why everybody should become a scientist story, is on my paid vacation to Hawaii my first year of grad school, I was working with, or somebody else was there who worked with the people from Cassini, so the Saturn mission, and we were there as Huygens was dropping down into Titan, and seeing the pictures for the first time and not knowing what to expect and having what the pictures were be beyond what you could even imagine. So that's what I'm waiting for, is for Brittany to send me the unauthorized Ceres pictures early.
And
can I get them too?
Yeah, being like, could you have ever imagined? Yeah, basically I can't wait to be astounded, because it's just kind of how every single step we take in space seems to go, is we see something that we wouldn't have predicted. So
very cool, very cool. Yeah, 2015, the year of the dwarf planet. We'll have Dawn getting to Ceres, and we'll have New Horizons getting to Pluto. So it's going to be pretty exciting. Again, like I told the Dragon Con Space Track crowd this weekend, I'm excited to see brand new worlds for the first time, because I wasn't around to see the Voyager missions, hit those outer planets. I'm sorry. To see those happen and first come in, so I'm excited for that. Anyway. Okay, thank you all so much for joining. We have Whitney Cobb and Judy Conley, who's also hanging out in the back, helping us with the hangouts and the comments and all that good stuff. Katie Dyl, who joined us from the wee hours of the morning of Curtin University.
12 hours difference.
Thank you again.
Oh, and let's go Buffalo. Please root for the Bills. If you don't have a football team, we need your help.
No comment, says the Jets fan.
Oh man.
You win.
So, sorry, sports ball. What's that? Andy Rivkin for showing us these awesome spectra of Ceres and the exciting work that's being done from your living room, from your living room and the top of Mauna Kea, which is fantastic.
That's right. Thank you for
And
having me.
Brittany Schmidt, once again, thank you so much. Awesome job running these hangouts and helping us out with everything. So thank you everyone for watching. Please visit us at CosmoQuest and visit the Dawn mission pages, and we will see you next time. Bye-bye.
Thank you.
See you, everybody.
And you can use the event page on Google Plus for questions there, or you can use the YouTube comments if you're watching this on YouTube, and we will be monitoring all those places. So feel free to join in the conversation and ask any questions as we go along. So why don't we get started right off with Brittany? Wanted to give us a brief overview of Dawn and how it relates to Ceres.
Sure. So it's a pleasure to be joining you guys again. Last time we chatted, I got to tell you a little bit about kind of my interests in Ceres. And today we've got two really great experts and friends of mine. Andy Rivkin is at Johns Hopkins Applied Physics Laboratory, so in Maryland, and Katie Dyl, who is actually a UCLA grad who is now doing a postdoc at Curtin University in Perth, Australia. So Katie's a meteoriticist and Andy is a spectroscopist, and they both study asteroids and the early solar system using a variety of different tools. So we thought they'd be really great perspectives to share the story of Ceres and what we're looking forward to with Dawn. But for those of you who may be new to the Dawn mission, it is a spacecraft that has just finished up a little over a year of observations of asteroid Vesta. It's actually the first spacecraft that's gone to one target and then left that target and gone on to orbit another one. So we're actually in the middle of our flight to Ceres, which, as we mentioned, will
Yay, we have everyone back. Everyone good with audio?
Think so?
I think so.
Awesome. Cool. Okay, hi everyone, and welcome to the special edition Dawn Hangout. This is Ceres, Great Expectations. So this is part 2 in our Ceres series. Yes, we are calling it that because why not? I am Nicole Gallucci. I am postdoc with the CosmoQuest Citizen Science Project, and I am joined by Brittany Schmidt from Georgia Tech. Hello. And I also have Whitney Cobb here from the Dawn EPO mission team, and she will be helping us track comments. And our 2 special guests today are Katie Dyl.
Hello?
So, hello, Katie. And Andy Rivkin.
Hi.
And they are going to be telling us a little bit more about how we know what we know about asteroids and Ceres, and why we're so excited to be getting the Dawn spacecraft to Ceres in early 2015. So I want to let you guys know, if you want to send in questions or comments for everyone here in the show, there's a couple of ways you can do that. If you're on Twitter, you can tweet at NASA_Dawn, and so we'll be monitoring that, answering questions there, as well as sending them along to the Hangout.